Hello, everybody, and thank you for being here. Welcome. Yeah, as part of our ongoing series of CRC seminars, we have the privilege to welcome today Sofía Celi. She's a cryptography researcher and an implementer at Cloudflare. She also currently leads the design and development of OTR version 4, the messaging protocol. She's also involved in helping to end gender-based violence and the use of digital tools that are used for that in the global south. And she's quite interested and always open to discuss different topics from programming languages, compilers, usable security, privacy by design, post-quantum cryptography, and any real-world application of crypto. She's also the co-founder of Crypto Latino, which is a hub for Latin American cryptographers, and she's also the main organizer of the Crypto Latin workshop, co-located with Latin Crypt this weekend, to which all of you are kindly invited. So without further ado, I give the floor to Sofía so he can tell us a little bit about Oblivious PRFs, what they are, and some new constructions and some new cool applications. So thank you, Sofía, for coming, and the floor is yours.
Thank you so much, Abdel, for inviting me, and also for the whole group for having me here. It's really nice. I'm going to share my screen now. Okay, I should be working now. So hi, everyone. Thanks so much for the introduction. As Abdel was saying, today I'm going to be talking mostly about OPRFs. At the end, you see in this title that it's about what they are, the new construction and new applications. But I also added at the end of this presentation the future, what things you might be interested in looking, if you're interested in researching on someone, or what open problems there are of OPRFs that you might be interested on digging a little bit more. Just I added those slides just in case you're interested in seeing something to work on. So Abdel already said, this is me, and you already know it. I mainly work at Cloudflare these days at the amazing cryptography research group. Now I'm working mostly on post-quantum cryptography, but I love other kinds of constructions as well. You want to learn more about me, that's the website on these slides. So now let's go directly into the presentation. I just put it a little bit of an agenda today about the definition, certain applications of OPRFs, the limitations that they have for a new implementation and practicality perspective. If you actually deploy, for example, OPRFs or implement OPRFs, what kind of limitations you have. And then, as I said, I also added these extra slides about the future. What will you, if you are interested in investigating and researching about OPRFs, what will you be looking into, or some open ideas that you can take to look into? So let's just go directly then. So what are OPRFs? Just added this in case someone might not be aware of what an OPRF is. An OPRF is basically the acronym that stands for Oblivious Pseudorandom Function, which is basically a two-party protocol, because it's always going to be executed between two parties, most of the times between a server and a client, or sometimes they call the client a user, but it's always going to be between these two parties. And the idea is basically that one party, in this case, the server, holds the PRF secret key, and the client holds the PRF input. And the obliviousness property that comes from it, the reason why it's not only a PRF, but rather an OPRF, is because it's ensured that the server does not learn anything about the input of the client, and the client in turn does not learn anything about the server secret PRF key. So therefore, they both arrive to the same output of the PRF computation, but they both don't know what the input was or what the server's secret key was. There's also another extra notion, which is the notion of verifiability that we will see in the next slides, where there was such a thing as a need for verifiability. But basically in the setting is that you can actually verify, the client can actually verify that the server's output is indeed the result of evaluating the underlying PRF key, which is the public key from the server. And we will see in the next slides exactly what a BOPRF is. So just to give you a little bit of an historical background, if you go for one of the first papers in which is kind of define what an OPRF is, there's older papers than the one that I have listed into this slide, but this is one of the one that gets quoted the most because it's where it was actually properly defined, the OPRF. So basically what is the idea is that, as I said, you have a protocol between the two parties, the server and the user or client. And as I said, the server holds the key, the secret key for the previous function, and the client holds an argument, the input, as I said on the previous slide, on which this function should be evaluated. And at the end of the protocol, the user, the client learns the output of that function, and is convinced that indeed that was properly evaluated. And the server should learn nothing, should learn nothing about the input that was passed to the function itself. So on this paper that I told you about, specifically in the paper that I'm listing, specifically in the paper that I'm listing into these slides, when they try to actually apply this idea on an OPRF to an actual real world construction, for example, an applicability into the password world, when they actually try to apply this protocol, they found some initial limitations. And one of the limitations that they have is that this construction that was presented in the previous papers that I show in the previous slide, they say that it did not imply security when several OPRF instances are executed concurrently. And there's also a need for an authenticated channel. So specifically in the password world, in order to correctly execute an OPRF, you need an authenticated channel to be from which the different messages in OPRF will be sent. So they say that that's actually a limitation. And that's why they propose the solution, which is basically the BOPRF. So what's basically this BOPRF is a verifiable oblivious pseudorandom function in which the server who generates the PRF key also produces a function description, and it's called, in the case they call it pi, which fixes a deterministic function, the deterministic function f. And the BOPRF functionality ensures consistency between the different rounds of the BOPRF instances executed on the same description pi, as well as the verifiability that the output value is computed using the commuted function f. So basically what they wanted this is because they wanted a way that you can actually verify whatever you're executed in the OPRF, instead of having to rely on the authenticated channels in order to be sending, for example, in the case that they were talking about, in the practical case that they were talking about, which is in the case of the password. So basically, as I say, what are the OPRF? What does this mean if we read this description that I previously quoted from the paper? That basically what you're going to be adding to an OPRF construction, you're going to be adding this descriptor pi, and this is just basically a fixed descriptor that works as a commitment to the key case. So this is basically saying that indeed the server holds the private key corresponding to the public key. If you can say that this adding these verifiability properties that the OPRF is very similar as thinking as if this works as a digital signature, because then it can be verified that the output is the correct value that you're supposed to be arriving during the OPRF execution. But it is again in a blinded manner because again the server does not learn anything about the client's input, and the client in turn does not learn anything about the key that the server holds. So it's still, this is a way that you can verify that indeed what you arrived, you verify that the output of the evaluation was indeed corrected, but you will not still be learning anything about what has to remain hidden as part of the OPRF protocol. So those two properties are still remain. Okay, so basically that's just very fun and very easy to understand, and one can see that this is indeed a very simple construction, a very simple algorithm to actually be using, but what actually makes it really interesting is it has a lot of application in the real world. So as I said already, one of the first papers we started looking at OPRFs and how can they apply into certain real world systems was this paper that was trying to apply it into the password world. And this has been expanded in several other papers. And indeed, there's a really interesting construction by the name of OPAQUE that tries to apply this idea of OPRFs into the password world, again, with advanced security properties. So as I said, one of the first applications was password protected systems. And why you actually want to protect the password protected systems, because in the systems that we have nowadays that we use for passwords, if you compromise the server, you will get access actually to the password file. And most of the times this means that you have to be protecting the server that holds all of these password files, or you will having to protect that specific instance inside the server that holds the password file. So for example, you will always have to be putting into a secure location in the server, so in order to not get compromised. But in practice, most of the times that we have seen attacks in the real world, these attacks indeed happen. Like attackers actually get access to the servers, and a lot of passwords get leaked from those services. Even if the passwords that are on the server are encrypted or salted, there still can be guessed, because there's a lot of ways to do this by using, for example, an offline dictionary attack and just brute forcing with several guesses of the passwords in order to eventually guess what the correct password is. And this has happened many times in practice. Another problems with actually using something as password systems is that if you use, for example, certain kinds of authentication to arrive to a more protected system, more password protected system, you can use something, for example, password-based TLS. And this is indeed a good thing that you should do if you're going to be use passwords, and maybe put it on TLS already. But this also means that at a certain point, the server has to see the password in plain text. At least once the server will have to see it in plain text, which can be difficult because first, that password, if the server saw it indeed in plain text, means that maybe that password can be cached or can be incorrectly locked somewhere, and that could lead also to a leakage of the password itself. And also there's the inability to actually, from the client, to actually check if indeed the server is encrypting the passwords or not. Meaning, for example, the server can be saying that yes, they're encrypting and salting correctly the passwords on their storage, but there's no way that the client can verify that. And indeed, it has happened in the real world. It has happened that there has been instances in which services were saying that they were salting and encrypting the passwords, when in reality they were not. They were just like encrypting them in plain text, and they found out later that they were being stored in plain text, because there's no way for the client to actually assure that the server is indeed taking these passwords and encrypting them in and putting them in a secure way in their storage. So there's no way to do that. And I say already that if you have an access to the password file after compromising the server, you can always do offline dictionary attack to try to guess the different passwords that were stored there. As I already said, after all of these attacks have occurred in practices, people have been already thinking about what kind of other security mechanisms we can put in place. So there's not much. So these attacks on passwords do not happen in the real world so much. So for example, an obvious application is this protocol that I told you about, which is OPAQUE. It's just an oblivious PAQUE, which idea is that indeed you're assured both that the server is not storing your password in plain text, because you're assured that they are always having only a representation, an encrypted representation of your password, of your password flow actually. And you also diminished the ability of actually execute offline dictionary attacks. In this case, I would like to say that OPAQUE is not completely perfect, because you can still do an offline dictionary attack, but not to the whole password file, but you will have to execute one dictionary attack per each user password that is stored on the server. So what happens in practicality with OPAQUE is that it diminishes the ability of an attacker to carry successfully a password dictionary attack, because they will need more time to actually execute it, because they will have to be doing per user in this case. So that's basically one of the novel applications in which you indeed can use an OPRF. And in the next slide, I'm going to tell you how the OPRF integrates into this password world, and in this idea, for example, of OPAQUE specifically. And if you want to learn more OPAQUE, this is the initial paper. There's also a standardization procedure currently at CFRG, if you want to see from more standardization process how it looks like OPAQUE in practice. So how does OPAQUE work? Basically, OPAQUE has two paths, two constructions. It basically has an OPRF and it also has a click. And in this case, let's focus on the OPRF because that's what interests in this talk. It's worth noting that also OPAQUE has two phases. It has a registration phase in which the user goes and registers the password with the server. In this case, it doesn't register exactly the password, but registers the authentication mechanisms with the server. And the second phase, which is the login phase, in which the user sends the password, and indeed the server matches to the authentication mechanism that was stored on them. And if they match, they have access to the service, and if they don't match, they don't have access to the service. So basically, those are the two phases that OPAQUE has. And in order to achieve those two phases, they use both an OPRF and a CLIC. So basically, on the first paper that you see that actually you apply OPRF into the real world, you see that the realization of the OPRF in a random oracle model is called a 2-hash DH. And we will see in the next slide what is called a 2-hash. But basically that they realize this in the random oracle model by using a group of prime order. So you will be using a lot of Diffie-Hellman operations in order to achieve the construction. And how does the OPRF work in the specific OPAQUE case is that you basically, the function is passed the server key, that this is a unique server key that's used per the user that is being registered by using the OPAQUE protocol, and the input, the secret input that is put into this function is the password that the user is providing to the server. So in this case, if we remember the properties from an OPRF, then the server should learn nothing about the password, and the client should learn nothing about the server key that is used for this function. So in this case, again, what we see is that we are achieving to the property that we didn't want to reveal the password to the server, not even once. In this case, we achieved to this property because the server is unaware of what the password actually is, but they will arrive to the same representation, in this case, to the same output that is called RWD, which is the one that is going to be stored encrypted in the server. But the password indeed is not going to be completely stored. Maybe what you're going to say is that a representation of this password, this RWD, is the one that is going to be stored on the server. So the server will not be looking at the password in plain text at all. And also the client is assured that the server is not storing in plain text their passwords, because they are sure that the password was never indeed looked by the server, so they know that it's not stored in a plain text. Therefore, what we are doing with this by usage of OPRFs is that we're increasing the security of the password world. So basically, how does it work in practice? We will actually instantiate the protocol in an actual construction. How does it work? Basically, if you see the OPAQUE paper, but also the OPAQUE from the standardization, you will see that it has three main functions: the blind function, the blind evaluation function, and the unblind finalize function. So basically, and the blind function is really easy. What you do is that you generate randomly a value, and then you take the input and you exponentiate it to this random value, and then you hash this random value. So one of the reasons that I tell you is that I told you in the previous slide is that I was going to tell you why this construction is called 2-hash DH. Is because you are basically using two hashes: a hash during evaluation and later a hash during the unblind finalize. So you have basically two hashes, and that's why it's called that way. So just to repeat, what does the blindness function do is that you basically have a random value that you generated. You take the password, in this case of OPAQUE is the password, you take that password and you exponentiate it into this random value. And you send the two values and you send the result of the exponentiation and also the random value. You only sent the result of the exponentiation to the other party, to the server in this case. So you're not revealing, again, what I say, the password at any point to the server, but rather you're sending this exponentiation to the password, this exponentiation of the password to this random value to the server. You send that to the server. The sender in turn, what it does, what they do is that they take this value that has been sent to the client and then they exponentiate it to the secret key. It's worth noting that in the case of OPAQUE, the secret key is generated per user. So the server will have to be generating this public key and server and secret key values per the user that gets registered in it. In the case of other applications of an OPRF, for example, in Privacy Pass or other kinds of anonymous credential, they are not going to be generating key pair per each user, but rather they are going to be generating a master key pair. But in the case of OPAQUE, which is the one we're talking currently, it's worth noting that they are going to be generating just a key pair per user that wants to register with the service. Okay, so in this case, they take the value that was sent by the client and they exponentiate it to this per user server secret key. If you want to achieve not only OPRF, but if you want to achieve a BOPRF, you also send a zero knowledge proof, a non-interactive zero knowledge proof. In the case of OPAQUE, this is not the case because we're not going to be using a BOPRF construction, but rather OPAQUE uses an OPRF construction. So they don't send the zero knowledge proof, but I just added this into this slide to make you look that it's really easy to make this protocol a verifiable one, because what you do is that you just only add this non-interactive zero knowledge proof, and that will achieve in turn the verifiability of an OPRF construction. When the server has indeed exponentiated the value to the secret key, they in turn send this value to the client. So then again, this preserves the property that the server will not be revealing their private key, because what they only do is that they send the exponentiation of the value that was sent with the client to their private key. What does the client do in turn when this indeed arrives to the client is that they do exponentiate it to 1 to the r, to basically to the value that they already know, and they will arrive to this value n. And then what they do is that they hash both, and this is the two hash functionality that I was telling you that they hash both the input and the value that they just generated, and they return this value, and then you know that indeed they have arrived to the output of the functionality itself. So as you see here on all of these functions that have now been divided between the client and the server, is that you indeed none of them learn any of the values that they're supposed to be remaining secret, but they both are going to arrive to the same output of the functionality. And this, for example, happens on OPAQUE in the moment that you want to do a registration. Instead of putting, for example, an X input to the blind function, what you're going to be passing as a user is indeed the password. And what you're going to indeed passing as part of the blind evaluation is the per user key that was generated by the server. That's just the difference. Okay, so that was indeed one of the applications of an OPRF. Just to tell you a little bit more, this is not only what happens in OPAQUE, it's not only this, meaning that first you do this OPRF, and for example, with this, you manage to register a password with the server, right? Because then after this OPRF has been executed, what you do is that the user creates their own key pair. With that key pair, they encrypt the output of this function, and they also encrypt the public key of the server, and they send that encrypted representation in turn to the server, and that's what is going to be stored by the server in turn. Once, for example, a user wants to log in now with the same credentials that they use, what they're going to be doing is that they send the same password, and the server is going to check that indeed it matches what was previously done by the OPRF. And then indeed, if everything matches, they're going to start the A-key channel for the login process. So basically, that's what basically OPAQUE works. But I just wanted to clarify you from an OPRF perspective how actually the OPRF works in the OPAQUE case. So what other applications of OPRF are? In the case of OPAQUE, one say that it's a kind of a real world application, but up to this point, OPAQUE has not been really put into a production service at the moment. There's some efforts from several places to indeed put OPAQUE into the real world. Another WhatsApp actually is checking how to use OPAQUE for certain of their operations, but not that much. It has been the idea to actually put it on OPAQUE in the real world. One application that indeed is put it in the real world is this construction that is called privacy pass. What does this privacy pass is? I basically have noted here in this slide the initial paper of privacy pass if you're interested indeed in learning more about it. But what's basically the idea of privacy pass? Why does privacy pass exist? The idea was basically that sometimes, for example, you have certain IPs that are considered to have a bad reputations, and those IPs are added into block lists. And therefore, every time that, for example, this specific IP tries to access a service that a server holds, what is going to happen is that they are going to be presented with a challenge each time. In this case of a challenge, for example, the challenge can be a JavaScript challenge. It can also be a CAPTCHA. It can be lots of types of challenges. But the one that is mostly used nowadays is this idea of actually using a CAPTCHA. The problem that if you are an IP that has a little bit of a bad reputation, tries to access a service, and you're presented every time with a CAPTCHA, is that the usability degrades, because a user will have to be solving a CAPTCHA every time that they visit a service. And that from a usability perspective is not really good, because users really don't love to be solving CAPTCHAs every time. So the idea is that instead to having to use this CAPTCHA and these challenge-based solutions, that you use something as tokens, anonymous tokens, in order to achieve authentication, but in a different way. To say that indeed you are an honest party because you have indeed solved the challenge. So the idea with Privacy Pass is that at first you are presented again with a challenge, with this CAPTCHA, for example, you solve it, and therefore you prove that indeed you are an honest participant that is trying to access this server. And once you have solved this CAPTCHA, what happens is that if you have installed Privacy Pass will generate tokens for you that you can indeed use later in an oblivious way, in an opaque way, to access the service. So instead of having a second time to solve this CAPTCHA again, what you are going to be doing is that you take from a storage this anonymous token, and you're going to be using this anonymous token to access the server. And in turn, what happens in reality is that the user does not see this at all. It's not that the user has to go on to, I don't know, to the browser, say like, hey, now instead of solving this CAPTCHA, I want to use an anonymous token. What happens in practice is that the user first solves a CAPTCHA, and then the next time that they visit that website, for example, what happens is that immediately on the background, the browser, instead of presenting the CAPTCHA to the user, sends the anonymous token to the server, and then they have access to the service. So it's kind of oblivious to the user in the sense that they don't have to be doing the action of either solving a CAPTCHA or either sending an anonymous token to the server. The browser will do it for you. So what's basically then the Privacy Pass is this idea of to generate cryptographically blinded tokens that can be signed by servers following some receipt of authenticity. In this case, the receipt of authenticity was the idea, for example, of a CAPTCHA solution. So once a client has indeed solved a CAPTCHA solution, then the server creates all of these blinded tokens, these anonymous tokens that are going to be used every time that you access the they access the service in the future. It's worth saying that there's two important properties if you're using any kind of these anonymous blinded or tokens / credentials, because in the literature they call very different ways. The two important properties that you will have to have. The first is unlinkability, meaning that once you get issued this token, you're going to be issued, and this tokens is going to exist somewhere in your browser, in your storage capability of your computer. These tokens are going to exist. And then, of course, when you want to re-access this service a second time, you're going to fetch that token from your storage, and you're going to be using that into this new service. But it should be really important that these two actions, the action of issuing one of the tokens and then the action of redeeming this token, should be unlinkable, meaning that no one else who is looking at this, or even the server who is looking at this interaction, should indeed be aware that this was the client to which you issue a token, and this is the client who is redeeming the token later on. Those two actions should be unlinkable, so it preserves the anonymity properties of the client in this case. Another important property is the property of unforgeability. In the case that when you get issued, for example, this X amount of blinded tokens, the client should have no capability of generating an extra token from this token. So if you are provided, for example, 5 tokens, there should not be the capability of the client to create a 6th token that they can indeed use. There's no way to do that. So if you read in the literature of all anonymous credentials, most of the time they want to achieve these two properties, unlinkability and unforgeability. Sometimes in several different papers, they are called different ways. Unlinkability is sometimes called privacy preserving mechanisms or something similar, but they mainly refer to this idea of the unlinkability and unforgeability properties. As I say, in Privacy Pass basically has two phases, the issuance and redemption phase, and these are the ones that should be unlinkable by someone looking to this connection, or a malicious server that is indeed trying to link issuance and redemption from certain clients that are using the service. And in these two phases, basically what they use is that they use this construction, they use the OPRF construction, they use the general OPRF, but they also added the zero knowledge proof that I showed you in the previous slide in order to achieve verification of the functionality. Okay, and that actually all looks well, and there's actually real world applications. Things has been going well for a while in the usage of all of these services, and we see that we arrive into interesting security properties from a password level, right? If you use OPRFs in a password world, we know that the passwords are not stored in plain text, for example. If you use OPAQUE again, you know that the server never sees the password in plain text. You know that it's really difficult to do an offline dictionary attack because you will have to do an offline dictionary attack per the user that use the services of the server. In the case of privacy pass, you see too that you arrive to certain privacy properties because you arrive to the property of unlinkability, meaning that no one is going to be linking the traffic that you are currently visiting. So you see that it has a lot of real world actual applicability and really interesting security and privacy properties that OPRFs arrive. What has happened in practice is that when we have actually constructed and implemented this application, certain kind of small issues have indeed arrived. And I thought it was really important to say this today, to see that it's not, even though these are providing really good security and privacy properties, they indeed have certain limitations. So as I said, for example, there's the case of malicious servers. So there could be the case, for example, that there's a privacy pass malicious server that indeed wants to link issuance and redemption phases. They actually want to do that. So what they can do in practice, for example, is that in privacy pass, on the contrary, when you compare this with OPAQUE, as I said in OPAQUE, the keys that you're going to be used for an OPRF are generated per user, meaning that you're going to have a key per user that is registering with the server. In the case of privacy pass, this is not the case. What you're going to have is that you're going to have kind of a master key pair that is going to be used. So what is the problem of having actually this master key pair? Obviously, that if this master key pair in privacy pass gets compromised, or you are suspected that the key can get compromised, if you are only using one key pair, then it's bad, right? If you compromise that key, what happens is that you compromise it for the future and for the past. So in practice, what happens in privacy pass is that that key is eventually rotated. It's rotated, for example, X amount of weeks. The master privacy pass key will be rotated. But in practice, this also opens the avenue for another types of attacks. So what can happen in practicality, for example, is that a server can decide, oh, I'm just going to be rotating the key every 0.5 seconds. And this means that the privacy pass server, in that case, can be able to link issuance and redemption because they will know that all of these tokens were generated only by this specific key, and therefore they can be indeed be linking issuance and redemption. So that's, for example, an avenue that can't get opened up because of the practicality that you need indeed to be rotating this master key. But if you rotate too often, then you're going to be going against the unlinkability property. So that's, for example, a limitation in practice. As I said here in the slide, this is not an issue in OPAQUE because in OPAQUE you have a key pair that is indeed generated per user. So as I said already, when I was talking about the first limitation, there's the other limitations, the limitations of key rotation, because as I said, in the case, for example, of privacy pass, you will be needing to rotate the key once an X amount of time that is good enough so it doesn't kill the unlinkability properties. But in the case of OPAQUE, maybe you should also be rotating the key. In the case of OPAQUE, it's a little bit more difficult because what you will be having to do is to rotate the key per each user that is registered on your server, which can be a little bit cumbersome. You can indeed ask, for example, each user to rotate the key. You're going to be asking actually each user that is registered on your server that you're going to be rotating your key and that you're going to be re-registering them with this new key that the server has assigned. So it could be in practice a little bit cumbersome, a little bit not so usable for users to be being asked to indeed to rotate the keys. And again, what I said instead on the case of privacy pass, will be the server's responsibility to rotate the master key every X amount of time. That will not be killing the unlinkability property of the OPRF. But I said also that there's a limitation on the usage of this user key pair that is indeed gets used in OPAQUE. So what happens, for example, when you have a per user key that you will be using per user in an OPAQUE service is that indeed it's very difficult to rotate the keys, or from an implementation perspective, it's really difficult, for example, that the server don't mess up all of these keys that they have to keep track of from the different users that they are registered. So for example, let's say the case that you have user Alice on your service, and then you have a user Bob on your service, and somehow the server messed it up, and instead of assigning the correct key from Alice to Alice, they assign the key to Bob, the Alice key to Bob, and that can happen in practice, and that can open actually the avenue to all kinds of attack. So as you see, both of the options are having a master key in the case of privacy pass, or having a paid user key in the case of OPAQUE, can have its limitations and practicality because they all open certain avenues for attacks into the protocols themselves. Another important limitation is the idea of double spending, and this is important when talking about anonymous credentials, when talking about privacy pass, in the sense that, for example, you are given to the client a token, and this client is going to be using the token in order to bypass later the challenge that is presented by a server. But what can happen in practice is that, yes, this client used the token, but it doesn't mean that the token disappeared. This can actually use the token again and have, like, for example, only one token that they are going to be using for everything. So we actually wanted to limit this double spending ability. And what in practicality in the privacy pass documents that right now the IETF is currently standardizing, what it says that every time that a server, for example, sees a token that is being used by a client, they put it into a strike list, they put it into a list in which they say, oh, this token was spent already. In practice, also what this results on is that the server has to do this additional verification to see if the token was used or not. What can happen also in practicality is that maybe you are talking to a malicious server who is not interested in having this double spending mechanism, and therefore our client is also able to use the token several times because the server doesn't indeed have this protection. So there's a lot of avenues to indeed research how to better prevent this double spending issue that you can have in anonymous credentials or in general in privacy pass. And the last really interesting attack that has been the result of some research that we have been doing is this idea of a hoarding attack, a farming attack. So what does this happen? How does this attack happen in practice? So as I said, in privacy pass, you are given this specific token, and this token is going to be in your storage for forever, basically, because the tokens don't have an expiration time, which means that in practice, the client can hold as many tokens as they want, right? They can always say to the server, I'm going to be solving more and more captchas, and you just give me more and more amounts of tokens. And eventually, let's say that they amount to terabytes of tokens. What they are going to be doing is that they're going to be taking those terabytes of tokens and spending them all at once with the server, which means that they are trying to do a denial of service attack against the server. And because the verification times can take a little bit of time, the verification times of the tokens can take a little bit of time on the server as well, what they will be achieving is a real world denial of service attacks. And because there's this notion of the expiration of a token, these clients can indeed be using tokens that they hoarded from years ago into an attack that they do today. So in practice, that can indeed happen. There's certain prevention mechanisms that currently exist in privacy pass and certain other anonymous credentials protocols that exist out there. One of the mechanisms to prevent this is, for example, the usage of the key rotation. So the use of key rotation is not only, for example, for saying, yes, we need to rotate the key because the master key in a privacy pass protocol can get compromised, but also to prevent a hoarding attack. How do you prevent a hoarding attack by using key rotations? What you do is that you will have only an X amount of tokens that were issued by this specific key. And once the server rotates this key, all of the previous tokens that were issued during the previous epoch in which this master key was indeed valid are going to be expired and they're going to be not valid anymore. So in that way, you're adding an expiration time to the token that is linked to the amount, to the epoch number in which you're actually rotating the service key. So let's say that you have a server key that gets rotated 2 weeks, then the tokens are valid only for these 2 weeks in which the key indeed was valid. And if later you try to access a server with this expired key, that doesn't correspond to the master key that indeed the privacy pass server has, then you know that this attacker will not have access to the service anymore because those tokens are expired, which in practice can reduce the feasibility of doing a denial of service attack with the usage of the holding the tokens. Because of this idea of actually having to rotate the key, every time that you want to actually have some kind of expiration, put it into the token, we actually thought of an alternative. Why we thought of an alternative? Because, as I said, rotating the keys is a good thing. You should always rotate keys in your systems. But what means in practice for an OPRF-based construction is that it could lead to linking attacks in which you can indeed link the issuance and the redemption phase, because you can always link that these tokens were issued and generated under this specific key that was valid for these 2 weeks, and that in practice can lead to these linking attacks. So maybe we don't want to always to be rotating the keys. What is this novel approach? This novel approach is actually called a POPRF, which stands for partially oblivious PRF. What that doesn't mean basically in practice is that you have the general BOPRF or PRF construction that I already showed you in previous slides. And what you do that you add this idea of a metadata attack. You add basically a tag, which can be a string representing something. And instead, for the blending functionality, you do exactly the same procedure. And from the blending evaluation functionality is that you do something different, because what you do is that instead of exponentiating the value that the client is going to send in you to the secret key, what you're going to be exponentiating is to an addition of the secret key plus the hash of the metadata, and you're going to be exponentiated to one over that value. And then you send that value in turn to the server, to the client, who will basically do similar operations. So you see the difference between the two protocols are very minimal, and it adds you the possibility of adding this metadata. So what is basically this metadata in practice? For example, in the case of privacy pass, what you want to add as metadata is this specific expiration. So for example, you will say, this token that I'm issuing you is only valid for 2 weeks. And that's actually indeed what you want to add as a string to this token that you're giving a user. And what it does is that it takes this metadata and makes it cryptographically bounded to the token itself. So once the server indeed verifies this token, they will know if they is valid or not. And it's really easy to achieve. You see, it's only an addition, some additional operations that we needed to add to the OPRF construction. So as I said, what is this metadata? In the case of privacy pass, why we added is to prevent against these hoarding attacks. And what we do is that we cryptographically link the expiration times to the tokens themselves. But of course, again, it has to have considerations against anonymity, because we cannot add explicitly, for example, that this token expires. This token was issued specifically on March 9 at 4 p.m. And with this amount of seconds, because then it's really easy to link between issuance and redemption against. So instead, what you want to be adding is something that is called an opaque metadata. And if you see, for example, on the privacy pass document, there's already a proposal to add this opaque metadata. How does this work? Is, for example, that the server will have their epoch numbers. They will have, for example, epoch 1, in which all of these tokens were issued. Epoch 2, in which all of these tokens were issued. So, for example, you take epoch 1 and you put this one as part of the POPRF construction, and this one in turn represents that this token is only valid during this amount of time. But it's really difficult then to link issuance and redemptions, because you know that this belongs to an epoch number in which a lot of other tokens, a lot of other clients could have been accessing the privacy pass server, and therefore you don't know exactly which one of those clients were the ones who were using this specific token. So in that case, you are diminishing the possibility of linking attacks while also preventing the hoarding attack. There's other ways that you can add metadata. For example, you can add metadata geographic localization. If you want, for example, on your token to be used in a specific region of the world, then you can indeed also use that. But when again, with considerations to anonymity, consideration to linkability, in the sense that you shouldn't be saying like, oh, add this metadata that this token was issued specifically on I don't know, in Ecuador, on this street with this latitude and longitude. You shouldn't be adding this explicit metadata, because then you are diminishing the linkability, the unlinkability / anonymity properties of the tokens that you issue. This metadata is also useful, for example, in OPAQUE, because what helps in practice is that instead of having to have a key that is generated per user, what you can use is that you can have a master key that gets used in OPAQUE, And then you add as metadata the user ID saying like, this token belongs to this user, this token belongs to this other user. And in this case, you will not having to have a key pair per each user that is using your server, which could be really good from an implementation and also from a storage perspective. And if you want to read more about this construction, you can find the paper over there. Just something that I forgot, this novel approach is called a 3-hash-DH because as you see, as I told you previously, this other construction was called a 2-hash-DH because it uses 2 hashes. And in this construction, we use 3 hashes because we are basically having to hash also the metadata that gets added by the server. So basically, that's are the novel applications of OPRFs. And I wanted, as I say, to add a small slides of the future, what you can actually start looking if you're interested in more research. The first one is, of course, if there's other applications of OPRFs. I know that right now there's a lot of people looking at actually how to apply OPRFs into different systems. There's a lot of efforts from Brave, from my team as well, and from different other paths. There's, as I told you, there's this interesting idea of WhatsApp to use the opaque mechanism for certain of the services. So there's maybe other application on this, in application in which, for example, you want to achieve unlinkability or privacy preserving properties, or in the case, for example, passwords that you want to achieve certain other security. So think about other applications and maybe these really interesting and really simple constructions can have. In the case of opaque, and in case this is an open question for all of the passwords and mechanisms that exist out there, is there really a way that we can prevent completely dictionary attacks? As I said, in opaque is more difficult to an attacker to actually achieve an offline dictionary attack because they will have to mount this attack per each user that registered their password in the server. But it doesn't mean that it's impossible. So is there a way that indeed we can prevent completely offline dictionary attacks, or is this something that is inherent to passwords themselves? In this case, maybe instead of using services that again rely on the password, maybe we should take a look into other services as, for example, WebAuthn or other forms to achieve authentication rather than passwords. For privacy pass and for general for anonymous credentials, something that is still open and is an issue that is still there is that, of course, I only show you the most basic construction of a privacy pass in which you have a server and you have a client. But there could also be a central server that issues tokens that various parties will be using. But in order to achieve this, you have to provide public verifiability because all of those parties should be able to publicly verify. And in this case, and the construction that uses privacy pass with OPRF doesn't really allow you to have this public verifiability. Is there a way that we can actually achieve this? Maybe there's a way, for example, by using blinded signatures, but there's still that's still up for question. And of course, something very interesting is the quantum world, because as I said, the OPRF is basically based on certain Diffie-Hellman assumptions, as you see, and you saw also on the protocol itself that is based on certain Diffie-Hellman assumptions. Sometimes some exponentiation assumptions. So basically, the idea then is that if a quantum ever exists, there is going to be also be able to break the OPRF constructions. So there has been other proposals. There's a really interesting papers of actually using a isogeny base in order to achieve an OPRF construction that is safe in the quantum world. The problem with it is that it uses C-side, and it seems to be that the security of C-side is still a little bit up to debate. So that is still a little bit up for debate then in turn. There's also a really other interesting construction that is based on lattices, but it uses a lot of zero knowledge proofs. So in practice, it can be a little bit inefficient. So if you want to learn more about them, I welcome you to actually read those papers and to try to think of actually efficient and safe ways to actually achieve OPRFs in the quantum world. Something really interesting that I was just recently reading is this paper about quantum annoyance. That indeed is an interesting property that was proposed as in the CFRG from IETF. It was proposed as a property that certain password-based authentication services should have. And basically what this property is that a scheme is said to be quantum annoying if a quantum computer can compromise the security of a scheme, but only by solving one discrete logarithm for each guess of a password. So this means that in practice, it will take a little bit of time, of course, for us quantum computers to solve the discrete logarithm, and then it will take them more time because they will have to be guessing per each password every time. So it will be annoying for a quantum computer to actually mount the attack. In the case of OPAQUE, it said that the OPAQUE, for example, is not quantum annoyance, but another mechanisms to achieve password-based authentication, such as CPACE, can actually be can actually have the property of quantum annoyance. But in general, maybe the question that you can ask yourself to actually generalize all of these notions is if in general OPRFs are quantum annoyance. Because if indeed OPRFs, you can prove that OPRFs are indeed quantum annoyance, then that it means that for certain protocols, for example, privacy pass, then even though they are going to be indeed be broken by a quantum computer, we can show that it will take a little bit more time for a quantum computer to break the protocol itself, which could be in practicality a good case to make. So I invite you, if you want to think about it, quantum annoyance and OPRFs is an interesting question to think about. With that, I think also one more time. So thank you very much.
Thank you, Sophie. Thank you so much for such a nice presentation. I think there is a question. If you want, I can read it to you, or I don't know if you have access to it now that you don't have the
yes.
slide. But yeah, I can read it if you prefer. It's Eduardo who is asking. First, he's saying, thank you for the great talk. He would like to hear your views on distributed OPRFs, which could be a fix for some of the issues that you mentioned, holding master keys, achieving proactive security, etc. Specifically, he has two questions. How does your approach compares to existing distributed POPRFs in terms of features? And the second, would it be easy to make a distributed version of your construction?
Yeah, so in the case of distributed constructions, it is true that it's more difficult to actually have these master keys because either you will have to be sharing them somehow, or the rotation process should be like also like distributed among everybody how you actually be doing. So in practicality, it can be a little bit challenging. In the practical world, we're also right now, that as far as I know, there's not in production a really, well, not a POPR, but also not an OPRF construction that is doing in a really big way with big traffic production ready case. So it's still something of an open question to see indeed what other limitations we have out there. POPRs, we haven't really thought about it in a distributed way, and it's an interesting line of thought. Right now, there's not actually a place in the paper where we thought about distributed systems for POPRF, but indeed that can be the case. I don't see here at the moment how you will be adding metadata can help into this, but maybe there's a way to actually achieve better properties if indeed in a distributed system, the metadata is also used for something on that. So I will have to think about it, but that's indeed an interesting avenue thought. Yeah, because right now the current construction that exists out there, privacy pass, is only sometimes used only by one master server, and then the clients are asking for the privacy passes. But what will happen in like under distributed systems where like there's more than only these two? So yeah, interesting question.
Okay, good. Another question is, what about real life deployments? How do you see it? What are the bigger roadblocks that you can have when you think about deploying this in the real world?
Yeah, so some of the ones that I've said, so for example, something in the real world that always took us a long time to get it correctly was this double spending mechanism, because it's really difficult to have a double spending mechanism. This list that you have like forever in storage somewhere can also be really vulnerable, for example, for a denial of service attack itself. So for example, let's say that you have this list of double spend tokens and you never delete it from storage at all. Then you will have this list laying around for like hundreds of years with a lot of tokens. So that in practice can be really bad. We don't know exactly, for example, when to expire this double spending list, when we should like delete all of the values and replace for blank ones. That is something that we don't know. We don't know what's the capabilities of the storage. If we can indeed have this list like with the terabytes of tokens or something like that, that just to check to double spend. So actually in practicality and from a research perspective, actually to think about how to better achieve double spending protection instead of relying on a list that you just go and check should be definitely something better. In practice, also certain abuses do happen. As I said, sometimes there's the possibility of hoarding, and indeed certain clients can indeed be hoarding certain tokens. So there's the idea of actually of adding some metadata came from that, of like actually saying like, hey, this abuse can indeed be happening in the real world, so maybe we should actually indeed be protecting it. The problem of actually rotating the key is also cumbersome, because rotating the key is also prone to failures. For example, let's say that the rotation of the key failed for some reason. That's an automated process, but it could fail for some reason. Then what is going to be happening in practice is maybe you didn't rotate the key, or like you are using not a key anymore, or using something else. So it can lead actually to problems. Maybe it can also lead to potential leaks of the key, because maybe you are loading that key from certain secure part of your architecture, rotating it and then loading it again to that secure part of your application, and that could lead to potential key leakage. So yeah, on practicality from an implementation perspective, those are the things that we have been finding out.
And in terms of performance, yeah, because
in terms
sounds
of
a bit heavy.
No, in terms of performance, actually, privacy pass is really good. The verification mechanism is the one that we were at the beginning. If you read the first privacy pass paper, you will see that they were a little bit worried about the verification times, because if the verification times are really big, then a hoarding attack gets even worse, right? Because if a client hoarded so many tokens for an X amount of time, and then they send that to the server, and the server takes a really amount of time to verify each token, then you actually arrive to that denial of service attack. And the privacy pass construction was constructed in such a way that the verification time is not heavy. So it's really, really easy. It's not heavy in the server or the client itself. The same for the OPRF. What we saw is that indeed it performs almost as the same as a privacy pass without metadata. And what we also found out is that it's better than use the blinded RSA or using any kind of other pairing options.